ChemicalBonding10 Hybridisation. The essential idea is that hybridisation results from the mixing of atomic orbitals to form the same number of new equivalent hybrid orbitals that can have the same mean energy as the contributing atomic orbitals. The nature of the science here is the need to regard theories as uncertain. Hybridisation in valence bond theory can help explain molecular geometries, but it's limited. Quantum mechanics involves several theories explaining the same phenomena, depending on specific requirements. Okay, covalent bonds and orbital hybridisation. If you recall S and P orbitals in atoms, in pure atomic orbitals look like this. We've got the spherical S orbital here, and we've got the three P orbitals that look a bit like dumbbells. These P orbitals are at 90 degrees to each other, and you can draw them on this plane as we do. Covalent bonds and orbital hybridisation. In molecules, bonds form when orbitals overlap. How do orbitals overlap to give these electron domain numbers and bond angles though? And you see this carbon dioxide has a electron domain of 2. There's 3 electron domains. This is 4 electron domains. And you've got this 180 degrees here. And you've got, 120 degrees. And here you have a 109.5, that tetrahedral angle. How do we reconcile our knowledge of atomic structure with molecular structures? They don't seem to fit together too well. So let's have a look. When many atoms form covalent bonds, the atomic orbitals in the valence shell blend together to form a new hybrid orbitals in molecules. So here you've got the pure atomic orbitals here. This is a s orbital. Here are the p orbitals. And over here we have a hybrid. It's an sp3 orbital. You see how it's kind of a small node here and a large section here and a central point there. This hybrid orbital has a shape and energy that's a blend of the s and p orbitals. The main type of hybrid orbitals in simple covalent molecules are the sp3 hybrid orbital, which has 4 electron domains, the sp2 hybrid orbital, which has 3 electron domains, and the sp hybrid orbital, which has 2 electron domains. There are more type of hybrid orbitals that, if you're curious, you can have a look at here. They're not on the IB syllabus. You've got sp3d hybrid orbitals, and you've got sp3d2 hybrid orbitals. Gives us a nice octahedral shape. The formation of sp3 hybrid orbitals. What's going on? You've got one pure s orbital, spherical in shape, and I'm taking the 1s orbital here, and you've got 3 pure p orbitals, which are dumbbell shapes, a figure of 8 shape. And it gives us 4 hybrid sp3 orbitals. The sp3 hybrid orbital shape and energy are intermediate between the pure s and p orbitals. All 4 sp3 orbitals are equivalent electron domains. So you can see the 1, 2, 3, 4 there in a tetrahedral shape. So this 1, 2, 3, 4 go in a tetrahedral shape here. The 4 electron domains are separated by an angle of 109.5, which by this point you should know as the tetrahedral angle. Some examples that have sp3 hybrid orbitals would be methane, which is tetrahedral in shape, ammonia, which is trigonal pyramidal, because it has this non-bonding pair here, and water, it has 2 non-bonding pairs of electrons. And so the molecular shape is bent or angular. Again, just a reminder of the angles. This 4 electron domains, methane, 1, 2, 3, 4, and 0 lone electron pairs. Again, 4 electron domains, 1 lone electron pair. Oops, the pen isn't working. There. And water has 4 electron domains, 1, 2, 3, 4, and 2 lone electron pairs there. sp3 hybrid orbitals form whenever there are 4 electron domains around an atom. all 4 sp3 orbitals with the 4 electron domains will spread out as far as possible, and this is what gives the tetrahedral shape for 4 electron domains. Other examples of substances with sp3 hybrid orbitals: diamond, you have sp3 throughout. All carbon atoms are bonded to 4 other carbon atoms. Therefore, you've got the tetrahedral arrangement throughout the whole gigantic structure, which is sp3 hybridization. And silicon dioxide here. All silicon atoms are bonded to 4 oxygen atoms, and you can see this blue silicon atom here is bonded to 1, 2, 3, 4 oxygen atoms. Therefore, tetrahedral arrangement. Therefore, sp3 hybridization. All oxygen atoms have 4 electron domains as well. They've got 2 bonding electron pairs to silicon. You can see this oxygen here is bonded to 1, 2 silicons. And it's got 2 lone electron pairs, which giving it a tetrahedral arrangement and sp3 hybridization. Okay, so when we're looking at the bonding here, we've got, in oxygen, we've got a 2s orbital with 2 electrons in it. And then we've got 1, 2, 3, 4 electrons in these 2p orbitals. And these all hybridize to give us 4 equal sp3 orbitals. And you can see we've got 2 unpaired electrons. These unpaired electrons can then bond covalently, so they're sharing with hydrogen atoms. And you get one bond here, another bond here. And so we've got 2 bonding pairs of electrons and 1, 2 non-bonding pairs, giving us the tetrahedral arrangement of the 4 sp3 hybrid orbitals. 1, 2, 3, 4 electron domains. Let's look at sp2 hybrid orbitals now. The formation of the sp2 hybrid orbitals. You've got a pure s orbital and plus 2 pure p orbitals to give us 3 hybrid sp2 orbitals and 1 pure p orbital. Okay, so 3 sp2s and 1 unaffected p orbital. The shape and energy of the hybrid sp2 orbitals are intermediate between the pure s and p orbitals, and this does remain unchanged. And so we get 3 electron domains from the sp2 hybrid orbitals that form sigma bonds. The pure p orbital can form a pi bond in double bonds. There's 3 electron domains. It's a trigonal planar arrangement with a bond angle of 120 between those electron domains. Examples with sp2 hybrid orbitals, you've got methanol and ozone. You can see here in green we've got 3 times sp2 hybrid orbitals, and we've got the 1 pure p orbital in purple. There's a 120 bond angle between the sp2 hybrid orbitals. And the sp2 hybrid orbitals form whenever there are 3 electron domains around an atom. All sp2 orbitals with the 3 electron domains form sigma bonds that will spread out as far as possible. The pure p orbital forms a second bond in a double bond. This gives a trigonal planar shape for 3 electron domains. Some other examples of substances with sp2 hybrid orbitals. We've got carbonate ions, 1, 2, 3 electron domains. We have benzene, this carbon here has 1, 2, 3 electron domains. Graphite, 1, 2, 3 electron domains. All the carbon atoms are bonded to 3 other atoms. There's no lone electron pairs. Therefore, there's trigonal planar arrangement and sp2 hybridization. The formation of the sp hybrid orbitals. So this time we've got 1 pure s orbital, we've got 1 pure p orbital, and it gives us 2 hybrid sp orbitals and 2 pure p orbitals. The shape and energy of the hybrid sp orbital are intermediate between the pure s and p orbitals. The 2 p orbitals remain unchanged, And you can see we get 2 electron domains for these 2 sp hybrid orbitals that form sigma bonds. The pure p orbitals can form pi bonds in triple bonds or 2 double bonds. So there's 2 electron domains, the linear arrangement, the bond angle of 180. Some examples, we've got cyanic acid there and carbon dioxide. Here you can see the 2 sp orbitals in green along this plane, and then you have the 2 p orbitals there and there. That's 180 for the sp hybrid orbitals. Sp hybrid orbitals form whenever there are 2 electron domains around an atom. The 2 sp orbitals with 2 electron domains form sigma bonds that will spread out as far apart as possible. The 2 pure p orbitals form the second and third bonds in a triple bond, or the second bond to 2 double bonds. This gives a linear shape for 2 electron domains. Some more examples. Hybridization of carbon. Let's consider the valence electrons in carbon. So we've got 1s, 2s, 2p. You can see these valence electrons have 2s, 2p. The changes in carbon atoms bonds, let's have a look. We're only thinking about the valence electrons here. So you've got this 2s here, it's full, and you've got the 3 2p orbitals with an electron in 2 of them. The electron gets there's electron excitation, and one of the electrons in the 2s moves into this free p orbital. Now we're able to make 4 bonds by overlap of half-fill orbitals. That's why carbon can make this 1, 2, 3, 4 bonds. But we get hybridization, and the 2s and 2p become sp3 with 1 electron in each sp3 orbital. Or you can get sp2 hybridization and would have 1 p orbital remaining, or you can have sp, delete, which will have 2 p orbitals. Okay, so we've got the 2s, the 2 p orbitals, and the 3 different possibilities for hybridization: sp3, sp2, and sp. Let's have a look at ethane. How many electron domains around each carbon? 1, 2, 3, 4. Therefore, the hybridization around carbon will be sp3. Each carbon atom has 4 sp3 hybrid orbitals. All bonds are sigma bonds. You can see this s orbital from the hydrogen bonding with the sp3 of the carbon, and there's overlap there. The carbon hydrogen, the sp3 and s orbitals overlap, and the arrow is pointing quite clearly to the section of overlap. The carbon-carbon has sp3 and sp3 orbital overlap, so both of these are sigma bonds. Let's look at ethene. How many electron domains around each carbon here? 1, 2, 3. Therefore, the hybridization around carbon atoms will be sp2. Each carbon atom has 3 sp2 hybrid orbitals and 1 p orbital. We can see that the sp2 here and sp2 here overlap, and sp2 overlap, which is a sigma bond, and you've got an sp2 and an s overlap here for another sigma bond. However, you also have those p orbitals, okay, and those p orbitals, which are above and below, and this is a sigma bond going through the middle. So this sigma bond here is this one, and above it and below it, the p orbitals can overlap to make a pi bond. So altogether you have a pi bond above and below the carbon, and a sigma bond, which goes directly between from the sp2 to sp2. Another example, ethine. How many electron domains around each carbon? 1, 2. Therefore, the hybridization around carbon atoms must be sp. And each carbon atom has 2 sp hybrid orbitals and 2 p orbitals. So you've got an sp-sp overlap here, which would be sigma bond, and you've got a s-sp overlap here, another sigma bond, another one here. You've got the sp from the carbon and the s from the hydrogen overlapping for sigma bond. Then in blue and purple here, you can see the 2 pi bonds from the 2 p orbitals. So you have 1 sigma bond, 1 pi bond, and another pi bond, which is 3 bonds altogether. This is why it's a triple bond. Let's consider the valence electrons in nitrogen. You've got 1s2, 2s2, 2p3. So valence electrons here, you have 2s and 2p. What happens when nitrogen atoms bond? We're just going to consider the valence electrons. There's no electron excitation because all orbitals are already occupied. So hybridization occurs. We can get the sp3. One of these sp3 will have a pair of electrons. The other 3 have a single electron. We can have sp2. And we can have sp and p. Now let's have a look at oxygen. Again, just the valence electrons. Whoops. There we go. There's no electron excitation because orbitals are already occupied. Hybridization will occur, giving us sp3, such as in water. You've got sp2 and a p, such as in methanol. And spp is very rare. We don't need to think about that one. To summarize, single bonds have a single sigma bond in them. Double bonds have 1 sigma bond and 1 pi bond. Triple bonds have 1 sigma bond and 2 pi bonds. sp3 hybrids are blending of 1s and 3p orbitals, and they occur when you have 4 electron domains present on an atom. sp2 hybrids, the blending of 1s and 2p orbitals. 1 pure p orbital remains, and occurs when you have 3 electron domains present. sp hybrids, blending of 1s and 1p orbital. 2 pure p orbitals remain, and this occurs when 2 electron domains are present. How many sigma and pi bonds are in each of these molecules? What is the hybridization of the carbon and oxygen atoms? Have a think about that. Press pause and have a go. Okay. Well, there's 7 sigma bonds in this one. You can see them. 1, 2, 3, 4, 5, 6, 7. And 1 pi bond. There's a double bond there, which has a pi bond in it. What's the hybridization of the carbon and oxygen atoms? This carbon here, sp3. This one, sp2. Let's put those lone pairs in there. And so that will be sp2. And this one will be sp3. It has 4 electron domains. This one, 4 electron domains. This one, 3 electron domains. There's 9 sigma bonds in this molecule and 2 pi bonds. This carbon here, sp3, sp3. This one, just sp. It has 2 electron domains. This one, only 2 electron domains. Please go to these 2 links to go over this again, and you should probably watch the rich Thornley channel on these two as well. The animations on this second one here are well worth a look. Goodbye.